Hello, hello, and welcome back. We're continuing our adventures into derivatives by talking about straight line motion graphs today, which, okay, it might sound a little bit boring, but actually I love this stuff. We're going to be able to describe what a particle or an object is doing by reading a velocity graph. This is cool stuff. Particle motion. A common use for rate of change, or the derivative, is to describe the motion of an object moving in a straight line. In such problems, it's customary to use either a horizontal or a vertical line with a designated origin to represent the line of motion. On such lines, movement to the right or upward is a positive direction. Movement to the left or downward is a negative direction. And as we talked about last time, the function s of t gives the position relative to the origin of an object as a function of time t. So that's a quick introduction. Again, last time we were together, we talked about some of the meanings that higher order derivatives could have. And when you're talking about particle motion or straight line motion, then s of t is position, v of t, the first derivative, is velocity, and a of t, the second derivative, is acceleration. We're going to focus a lot in the velocity section today. Instantaneous velocity, that's a big deal. It tells us how fast something is going at that exact instant and in which direction it's moving. So if you have a horizontal line, you're going right and left. If the velocity is positive, then the object is moving to the right. If velocity is negative, the object is moving to the left. And if the velocity is zero, the particle is stopped. We can also have a vertical line, an up and down motion. If velocity is positive, that means the object is moving up. If the velocity is negative, the object is moving down. And again, if the velocity is zero, then the particle or the object is just stopped. It's just sitting there. This is very important. Speed does not indicate direction and is not synonymous with velocity. Mathematically, speed is not synonymous with velocity. However, in our just everyday English language, sometimes we use speed and velocity as synonyms, but we have to be very careful in calculus that we don't mix them up. So speed tells you how fast an object is going, no matter which direction. Speed is always positive. Mathematically speaking, speed is the absolute value of velocity. Acceleration. Acceleration, that's the first derivative of velocity, tells us how quickly something speeds up or slows down. It's telling us more specifically how velocity is changing with respect to time. So for a horizontal line, if acceleration is positive, then the velocity is increasing. If acceleration is negative, the velocity is decreasing. If acceleration is zero, that means there's no change in velocity. It does not mean that the particle is stopped. In a vertical line, well, it's actually the same thing. If acceleration is positive, there's an increasing velocity. If acceleration is negative, it's a decreasing velocity. And if acceleration is zero, there's no change in velocity. But now let's talk a little bit more about speeding up or slowing down, because that can get a little bit confusing. If velocity and acceleration have the same sign, then the object is speeding up. So if the sign of velocity is positive, the sign of acceleration is positive, then the object is speeding up. If velocity is negative and acceleration is negative, weirdly enough, the object is also speeding up. If velocity and acceleration have opposite signs, then the object is slowing down. So positive velocity, negative acceleration, that's a slowing down. And negative velocity, positive acceleration is then a slowing down object as well. Keep that in mind. Same sign, speeding up, opposite signs, slowing down. So in calculus, we're often asked to analyze motion graphs. But there's different kinds of motion graphs. Sometimes it's position versus time, and sometimes it's a velocity versus time graph. So for many graphs, the slope of the line and the area between the line and the horizontal axis have physical meanings. We're going to start with position versus time graphs. So this is down here. That's a position versus time graph because we have time on the x-axis and distance on the y-axis. So position versus time graph. The slope of a position versus time graph tells you the velocity. It also tells you the direction the object is moving, right, left, or not moving at all. The y-intercept of a position versus time graph tells you the starting point of an object. And then what is this? That says velocity equals change in position over change in time. So if the slope is greater than 0, the object is moving to the right or up. If the slope is less than 0, then the object is moving left or down. So in this particular position versus time graph, we have an object that's moving up or to the right. Now, velocity versus time graphs. Those are a little bit of a different beast, but they're so cool. So consider an object moving at a constant velocity of 5 feet per second. That's this top line up here. Since velocity is positive, it's above the x-axis, we know that the object is moving to the right. The question is, how far has the object traveled in 6 seconds? Perhaps you already know that distance equals rate times time. Position equals velocity times the change in time. So what do we know? Our position is velocity, 5 feet per second, times how long it was going that fast. And the seconds cross out, and what you're left with is 30 feet. That's an algebraic representation, but I want you to look at the graph. What is the area under the velocity versus time graph? This area, all this in green, what is that area? 5 times 6, the area is 30. So the area in that box there is a graphical representation of the distance traveled. This is very, 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 very important. In a velocity versus time graph, the area equals a distance traveled. Well, if the area equals distance, what does the slope of the graph tell you about the object? The slope tells you the acceleration. Very interesting. This graph here on the right, it's a velocity graph. It tells you that up here, v of t. So we have velocity on the y-axis and time on the x-axis. And the rest of this lecture, we're going to be analyzing this graph. So get comfortable. Anytime you're confronted with a graph, it's important that you label it so that you know what's going on. For instance, I'm going to label my graph right here. And this is telling me that it's a derivative graph. The derivative of the position graph is the velocity graph. Okay, so number one, when is the particle moving at a constant speed? Constant speed is a speed that doesn't change. So right here, there's no slope. No change in velocity during that time. So between 0 and 1. When is the particle moving to the right? The particle's moving to the right anytime velocity is positive. This is a velocity graph, so anything above the x-axis, whenever velocity is positive, the particle is moving to the right. So between 0 and 2 seconds. When is the particle moving to the left? Well, that's when velocity is negative, so anything below the x-axis. So between 2 and 5 seconds. When does the particle change directions? Well, that's when it's going to cross the x-axis or at the x-intercept. So at time t equals 2. When is the particle speeding up? So this is what we learned earlier. It's speeding up when the sign of velocity and the sign of acceleration are the same. So if velocity is positive, the slope has to be positive. Nothing there. If velocity is negative, the slope has to be negative. So right here, that's when we know that the particle is speeding up. When is the particle slowing down? Okay, now we need opposite signs. So if velocity is positive, acceleration has to be negative. If velocity is negative, acceleration or slope has to be positive. So between 1 and 2 and 3 and 5. Number 7, when is velocity increasing? So velocity increasing, the slope of the velocity function or the derivative of the velocity function needs to be positive. That's the acceleration greater than 0. So that's here between 3 and 5. It's the only positive slope on the graph. Number 8, when is velocity decreasing? That's when acceleration is negative or we have a negative slope. So that's going to be right here. Then again, right here. But there's not a constant slope. Something's happening right here. So we're going to say between 1 and 2 and then between 2 and 3. Now, number 9. This is a very important question. It says, is the particle slowing down on the same intervals that velocity is decreasing? In other words, is slowing down the same thing as a decreasing velocity? They're not the same thing, and that can be confusing. Number 10, how fast is the particle moving at the time t equals 4? So here's t equals 4. How fast is the particle moving? And in what direction? The speed is the absolute value of velocity. And at 4, our graph is at -5. So this guy is moving at 5 feet per second. What direction? Well, it's negative, so that means to the left. What is the particle's velocity at t equals 4? Well, now you take the absolute value brackets off, so the velocity is -5 feet per second. Number 12, what is the average velocity over the time interval from 2 to 3? So average velocity is going to be a change in position over a change in time. Well, how do you know the change in position? Well, remember, on a velocity versus time graph, area equals distance traveled. So the area here is the area of this triangle. That's the distance traveled. So the area of a triangle is 1/2 base times height. So this area here is -5. So it's gone -5 over 1 second. So -5 feet per second. Number 13, how far does the particle move during the first second and which way? So the first second, that area is represented by that square there. So 1 times 5, the area is 5. So I know that he's gone 5 feet to the right because it's positive. Number 14 asks, how far to the right does the particle go and when does it arrive there? Well, it's still going to the right up until time 2. So we need to add the area of that triangle there, which is 2.5. Let's clear this stuff up. Now, at time t equals 2, that's when the particle stops and turns around. That's when the velocity goes from positive to negative. So we know that at time t equals 2 seconds, the particle has gone 7.5 feet to the right. Then it stops and goes to the left. What is the total distance traveled by the particle? Well, we need a little bit more area to cover here. So that triangle is -10. So total distance is this area plus this area. Now, this area counts as positive distance. Why is that if it's negative? Well, think about if you walk a mile, if you walk 1 mile, and then you turn around and walk home, that's another mile. So left and right, you still walked 2 miles, right? So total distance is all the distances, the absolute value of all the distances added together. So add all those together, you get 22.5 feet. That's different than what number 16 is asking, which is what is the particle's position after 5 seconds? So he goes 7.5 to the right, then turns around and goes -15. So his final position is -7.5 feet. Are the answers to 15 and 16 the same? Let's go back. No, 22.5 is not the same as -7.5. Total distance versus final position. Those are different. What's the average velocity of the particle of the 5-second time interval? The average velocity, again, is change in position over change in time. Well, change in position, we just discovered, was -7.5 feet, and it did that over 5 seconds. So that's -1.5 feet per second. Number 19 says, what is the average speed over the 5-second interval? That's different now. It's total distance divided by time. So this time we use the 22.5 and divide it by 5. So 4.5 feet per second. Moving on to acceleration, number 20 asks, what is the particle's acceleration over the first second? 0. Acceleration is the slope of the velocity graph. So if there's a 0 slope, there's no change in velocity. Over what time interval or intervals does the particle have a positive acceleration? Again, we're looking for the slope of the velocity graph to be positive. So between 3 and 5. When is it negative? Well, we need a negative slope. So between 1 and 2 and between 2 and 3. When is the acceleration undefined? Remember talking about undefined derivatives before? That's when the slope from the left doesn't equal the slope from the right. So that's at 2. Oh, and it's here at 1 also. And down here. So time 1, time 2, and time 3. State an interval of time when the particle has a positive acceleration but is slowing down. So this is when we have a positive acceleration. Is it slowing down? Yes, it is, because the velocity is negative. It's below the x-axis. Almost done. State an interval when the acceleration is negative So that's when it's negative, but the particle is speeding up. Well, that means it has to match the sign of the velocity. So negative acceleration also has to be a negative velocity. So between 2 and 3. Number 26, what is the particle's acceleration over the time interval from 3 to 4? In other words, what's the slope right there between 3 and 4? It's 5, so 5 feet per second squared. That's the acceleration label. Number 27, what is the acceleration of the particle over the entire 5-second interval? To find that, we're basically finding the slope from point 1 to the last point. So just using this regular slope formula, you'll find a slope of -1 feet per second squared. And then the last question, over what time interval is the particle's velocity decreasing at a rate of 5 feet per second every second? So that's 5 feet per second squared. The velocity is decreasing. Okay, so another way to ask that is, where is the slope of the velocity? -5. So that would be right here between 1 and 2. It takes practice to be able to learn how to read a velocity graph. So it might be worth watching the video again, finding some practice problems, but once again, this is math, so practice makes perfect. See you next time.